All right, we're still talking probability, and let me just repeat the thing I said at the end of the last clip. And that is that if we have two random variables, x and y, then the probability that the pair xy lands in some part of the plane called D is going to be the integral over D of f, where f is required to be non-negative and have total integral equal to 1. And in this case, f is called the joint probability density function of x and y. All right, and so in this clip, when I say probability is normalized, I'm talking about this property right here, that the total integral has to equal 1. And so it turns out that it's often necessary to figure out just exactly what your PDF is. You might have some description of it, like perhaps you know that it should be uniformly distributed over a given region. Well, then that tells you that it's constant, but it doesn't tell you what the value of that constant is. But we can use this integral to figure that out. Let's look at what I mean by that. Suppose we know that we've got two random variables and they're jointly distributed with exponential distribution over the first quadrant. So it's going to look like c times e to the minus x minus y. That's going to be the joint PDF of x and y. And suppose that we know that y always takes a larger value than x. So we don't know what the value is going to be. It's totally random, but it's going to be bigger than x. So then, based on this, we can find the normalizing constant in the front there. So let's see. So all we have to do basically is integrate this function over the region and then divide by whatever we get so that it balances out to being 1. And so let's set up the region here. So we're in the first quadrant. So here's the x-axis and here's the y-axis. And this expression right here says that y only takes values of x. So that means that we only need to take into consideration this region up here. So this is going to be our domain D. And I think we're going to integrate dy first when we set up this integral. You can do it either way. I don't think it makes a whole lot of difference. But so the idea is that when we do the total integral, it should equal 1. So this region is, let's see, I always like to start from the inside and work my way outward. So we're going to be starting for a given slice on this surface right here, and we're going to go upward. So we're going to start at y equals x, and then we're going to go off, and we're going to just keep on going in that direction. So we're going to go all the way off to where y equals infinity. And then we're going to pick these slices up starting from the first slice right here where x equals 0. And then we're going to go that way, and we're going to keep taking slices forever. So we're going to go from 0 to infinity there. And then our PDF is c e to the minus x e to the minus y. And we're doing dy first, and then dx. Okay, so that's the hard part. I've got my integral all set up. Now I can just go about working this one out. So let's see. So this is going to be integral from 0 to infinity, and I've got that constant c, which I can stick anywhere. I could even pull it out front if I wanted to. Let me give myself a little bit more room. And then let's see, so I've got e to the minus x I can pull out of that inner integral, and then I've got the one that goes from x to infinity, e to the minus y dy dx. And so for this step here, I use the idea that e to the, I guess actually in the step previously, in order to get this, I use the fact that e to the minus x minus y is e to the minus x e to the minus y. So the usual exponential property. And then a couple times we did a shortcut where we did, this integral times this integral. In other words, I just pulled this one outside. I cannot do that here because I've got an x, and I cannot pull an x out past an x right? So it is stuck inside, so I cannot do the shortcut. Don't make that error. It's an easy error to make. Okay, so let's see. So we've got C integral from 0 to infinity, and then maybe on the scratch paper here, I will do the integral from x to infinity e to the minus y dy. So that's going to be minus e to the negative y from x to infinity. And at infinity, e to the minus something goes to 0. So that's going to be 0 minus, and then I've got negative e to the minus, and then swapping x in for y, this guy. So that's actually just good old e to the minus x. And I already had an e to the minus x in there, so I can combine them and get e to the minus 2x. Here, I'll do it in 2 steps just to be coy. Okay, so on the next line of my computation, I have 1 is now equal to 0 to infinity e to the c e to the minus 2x dx. And so this is c, the integral of, and I've got minus 1/2 e to the minus 2x from 0 to infinity. And so that gives me c over 2. And so then cross multiplying the 2 over to the other side, I have that 2 is equal to c. And I'm done. That's my constant. So the joint PDF, in order for this to be a probability density function, it has to be 2 e to the minus x e to the minus y.